Bismillahirrahmanirrahim. Assalamu alaikum dear students. You are watching Study with Sheraz, and in today's lecture we are going to discuss about the mass defect and binding energy. This is going to be a very important topic in the nuclear chemistry. Just like as we know that our nuclei are composed of the large number of nucleons, that is protons and neutrons. And it is assumed that the mass of a nucleus must be equal to the sum of the masses of the protons and neutrons, or you can say the sum of the masses of the nucleons. Basically, it is observed that the actual mass of nucleus or the observed mass of nucleus is a little bit less than the sum of the masses of the nucleons. So why does this is happening? This is explained in mass defect and binding energy. So first of all, we would look at what is mass defect. Basically, difference between mass of a nucleus and sum of the masses of its constituent nucleons is known as the mass defect. As I have mentioned earlier that the mass of a nucleus is a little bit less than the masses of the sum of the masses of the nucleons. So this difference is basically known as the mass defect. So if we take the example of the helium-2, so this isotope is having 2 protons and 2 neutrons. So it is assumed that the sum of the masses of the 2 protons and 2 neutrons must be equal to the observed mass of the helium-2 nuclei. But when we look at the data, the fact is different from our assumption. Predicted mass is equal to 2 into 1.008 AMU plus 2 into 1.007 AMU. Basically, these are the values of the masses of proton and neutrons. So the predicted mass is equal to 4.032 AMU. So this is the value of the helium-2 nuclei that is predicted or calculated from the masses of the 2 protons and 2 neutrons. But if we look at the observed or the actual mass of the helium-2 nuclei, that's equal to the 4.002 AMU. So you can look at here that there is a difference between the two values for the helium-2 nuclei. So mass defect is equal to the 0.03 AMU. This is basically the difference between these two values, observed mass and that of the calculated or the predicted mass of the nuclei. So where does this mass goes? As we know that mass can neither be created nor can be destroyed. So where does this mass is going? Actually, when a nucleus is formed from its constituent nucleons, some of the mass is lost and a subsequent energy is released. So this energy is basically known as the nuclear binding energy. It says that whenever a nucleus is formed from its constituent nucleons, some of the mass is lost and subsequently a large energy is released in the formation of the nucleon, and that energy is basically known as the nuclear binding energy. Basically, nuclear binding energy is a reflection of the force that holds the nucleons together, or you can say that it's the reflection of the stability of a nuclei. How strongly the nuclei are bound or how strongly the nucleons are bound with each other, that is basically shown by the nuclear binding energy. Greater the value of nuclear binding energy, greater would be the stability of the nuclei. This is in accordance with E is equal to mc square. So this is basically the Einstein's mass energy interconversion equation, because this equation shows that mass and energy are interconvertible with each other. So mass defect and binding energy is in accordance with the E is equal to mc square, where E is the binding energy, m is the mass defect, and c is the speed of light or the velocity of light in the vacuum. It's an amount of energy that must be supplied to a nucleus to break it into constituent nucleons. Just like the lattice energy, the nuclear binding energy can be defined in another way, that it's the amount of energy that must be supplied to a nuclei to convert it into the constituent nucleons. Basically, we have first defined it in the terms of the building of nucleus from the nucleons that releases energy. And when we are going to break that nuclei into its constituents, the energy must be supplied. So it's the energy that must be supplied to break a nuclei into its constituent nucleons. So greater the amount of that energy, stable would be the nuclei. For helium-24, we can calculate the nuclear binding energy of helium-24 if we know two things. That one is the delta M, that is the mass defect, and the other is the c, that's the speed of light, and that's a constant quantity in the vacuum. So the only thing that we must know to calculate the nuclear binding energy is the mass defect, that is shown by the delta M. So in case of helium-24, we have calculated the mass defect. So that's equal to 0.03 AMU. And in order to convert it into kilogram from the AMU, we are going to multiply it with the 1.66 into 10 to the power minus 27. So this is converted into the 5.04 into 10 to the power minus 29 kilogram. This is the speed of light, 3 into 10 to the power 8 meter per second. So we put these values into the E is equal to mc square equation, and we get the value of the binding energy is equal to 4.53 into 10 to the power minus 12 joule. And most of the time, the nuclear binding energy is expressed in terms of the electron volt. So we are going to convert this energy into the electron volt. Since 1 electron volt is equal to 1.60 into 10 to the power minus 19 joule, we have a separate video on the electron volt, and that video is present at the end screen of this video, and link is given in the description. So you people must watch that video in order to get the idea of the electron volt. So E is equal to 4.53 into 10 to the power minus 12 divided by 1.60 into 10 to the power minus 19, and the answer comes 8.3 into 10 to the power 6 electron volt. And this electron volt can be converted into the mega electron volt, because 10 to the power 6 is equal to mega. So if we express this energy in the mega electron volt, that would be 28.3 mega electron volt. Average binding energy, this is another term that is very important. So binding energy per nucleon is known as the average binding energy. Just like that, if we are having 4 nucleons in the helium-24, so if we are going to find out the average binding energy in case of helium-24, we are going to divide this value with 4, and we would get the value in the form of the average binding energy. The average binding energy increases with increasing atomic mass, but decreases later. If we look at the trend of the nuclear binding energy, it is observed that in the start, it increases with the increasing atomic mass of the nuclei, but after a certain maximum value, it starts decreasing with the increase in the atomic mass of the nuclei. So we can make an idea that the nuclear binding energy is maximum for the nuclei with intermediate atomic masses. We have observed that the uranium that is used in the nuclear fission, uranium 92 238. So this is a highly unstable nuclei that is used in the atomic bomb and in the nuclear fission at power plants. So this is having very high amount of the atomic mass, and this is unstable. So nuclei with very high atomic mass and with very low atomic mass are unstable. We can plot a graph between the values of the atomic mass and the binding energy. On x-axis, there is the values of the atomic mass, and on y-axis, it's the nuclear binding energy. And it is shown here that with the increase in the atomic mass, it's increasing. And at the value of 56, it's maximum. And as we move further in the graph on x-axis, as the values of the atomic masses are increasing, the value of nuclear binding energy is decreasing. And at this maximum, iron is present. I have mentioned here that 56 iron. So iron is the most stable nuclei in all the naturally occurring nuclei or nuclides. Its binding energy is the 9 mega electron volt. No other nuclei is having such a large value of the binding energy. So this statement is related to this graph. It says that earlier elements do fusion, but later elements do fission. As the nuclear binding energy is small with small atomic mass nuclei, so earlier nuclei try to perform fusion, and during the course of fusion their masses would increase, so they would get the higher binding energies. That's why the earlier elements perform fusion reaction like the hydrogen, helium or some other nuclei. But after this maxima, as the atomic mass is increasing, the binding energy is decreasing. So later elements perform the fission reaction. And as I have mentioned earlier that uranium-238 or the other isotopes of the uranium-235 to 36, these are best used for the fission reaction. Why? Because their atomic masses are very high, and during the process of fission reaction they decrease their atomic mass to increase their binding energies. So this was all about the mass defect and binding energy. If you have any question related to this video, you can post your question in the comment section. We will meet in the next video. Up till then, Allah Hafiz.